that we studied all our different geometries, let's take a look at valence bond theory and start to understand some of where we try to piece together what we see versus how we model it. Because when we look at just the base electron configuration of something, it doesn't always explain everything that we're seeing. So let's take a look at methane, and we'll start there. And we'll see if from methane, we can then start to put a bigger picture together. All right, so when we look at methane, CH4, we've got a molecule that flat looks like this. Okay, that's our Lewis structure. When I try to put together my 3D representation of it, we have something like this, like that, okay? So I've got that carbon there that has 4 bonds around it. Now, when I look at my just dot model of carbon by itself, we know that carbon has 4 valence electrons. And so when we put our Lewis dot diagram for carbon together, we do this, where we represent, okay, each unpaired dot represents a spot where it can pair up with another electron and form a bond. When I look at the electron configuration of carbon, I get 1s2, 2s2, 2p2, which looks like this. 1s, 2s, oh, I'm already thinking ahead to 2p, 2s, and then 2p. All right, so 1s doesn't matter when it comes to bonding because those are core electrons, right? When we're looking at bonding, we're considering our valence electrons. So when I do my valence electrons, I get something like that. Well, according to this picture, what's going on here? I have paired electrons in that 2s orbital and single unpaired electrons in 2 of the 3 2p orbitals. Does that explain what we're seeing with the carbon? How can I have 4 unpaired dots when this particular picture here only has 2 unpaired electrons? Okay. Now, not only that, but let's take it a step further. When we think about our orbitals, you know, my s orbital is like this. So I have 2 electrons that are sitting there in something spherical. You know, my p orbitals take on these sorts of shapes. Okay? I know those are kind of funky looking. But the point being is that when I overlap all of those, we don't get a situation where we have this, 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 and this. Okay? So how do we go from carbon's 4 valence electrons, an s orbital, and these p orbitals, to something where we can get 4 unpaired electrons and a tetrahedral shape? Well, that's where our valence bond theory comes in. Our valence bond theory is going to help us explain what we see by understanding that as atoms bond, different sorts of things happen. All right? So what we're looking at is we're visualizing the way this bonding takes place. We want to explain, we want to understand, how do we reconcile what we see bonded versus what we know about something before it bonds. And so what's happening as it bonds? Okay, so our valence bond theory. Bonding occurs when an orbital of one atom overlaps with the orbital of another. Okay? And so we get this overlapping that happens. So the big question though is, as the overlapping is happening, what's occurring that then lets us arrange things such that A, we see the bonds that we see, and B, we see them in the geometric orientation that we see them in. Okay? So let's expand this further. Okay, so we have some things occurring. Now, when I have a base orbital, I'm going to have a spin up and a spin down, right? I can only put 2 electrons into each orbital. Well, the same thing is true for our valence orbitals. So what we're looking at is a set of overlapping orbitals has a maximum of 2 electrons that must have opposite spins, just like a regular base look at an atom. Okay. Now, when we have orbital overlap, let's think about this. The blank the orbital overlap, the stronger, more stable the bond is. So, do we think we need less overlap for a stronger bond or more overlap for a stronger bond? The more overlap there is, the stronger the bond. So the greater the orbital overlap, the stronger and more stable the bond. All right, when we look at valence atomic orbitals in our molecule, they are, do you think they're different or the same? So let's think about that. That picture that I drew for methane, when we have our S and our P orbitals, they're not arranged in a tetrahedral fashion. And in S, I have 2 paired up electrons, which doesn't help with, carbon being able to bond 4 times. So what do you think? The valence atomic orbitals in a molecule are the same or different from those in isolated atoms? What do you think? If you said different, you are correct. Okay. And so here's where we come down to our valence bond theory. Something happens to those atomic orbitals to form molecular orbitals. And what happens is a hybridization. So we get a hybridization of atomic orbitals to form molecular orbitals. Okay? Hybridization of orbitals. So when we start to look at this, all right, when I look at isolated species like hydrogen or hydrogen fluoride or fluorine, very simple. I only have 2 things bonded together. Anything where I just have 2 points, we get that straight line. So anytime we have orbitals overlapping, whether or not they hybridize, we get this overlap. We have an electron from one, we have an electron from the other. They spin pair in opposite directions, and we get this occurring. Okay? But once I move past 2 things hooked together, that's where we start to see all of our 3-dimensional geometries, and that's where we start to see this hybridization. So when I look at hybrid orbitals, there's some key points. All right, the first key point is when I look at the number of hybrid orbitals, they have to equal the number of atomic orbitals mixed. All right, so what does this mean? Well, let's say we go back to that methane. Okay, so that methane, if we assess the geometry, we have a central atom and we have 1, 2, 3, 4 surrounding atoms and no lone pairs. So that AX4, what does that mean? That means that I need 4 places to put electron groups around my central atom. Okay, I need all right, so we need 4 places to put electron groups around that central atom. And so the number of hybrid orbitals I obtain, we're going to need to mix 4 atomic orbitals to give us 4 places to put things. All right, so think about that. Okay, next up, the type of our hybrid orbitals is going to vary with the types of atomic orbitals. So when we think about this, how many basic molecular shapes did we have? We have linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. So that's 5 basic molecular shapes. We have 5 shapes that we know of where we need to have 2 places to put things, 3 places to put things, 4 places to put things, 5 places to put things, and 6 places to put things. Okay, so 5 types. So we should get 5 different types of orbital hybridization depending on what we're mixing. So in carbon, okay, in this methane, again, our valence electrons was at 2s2, 2p2. We have our 2s and our 2p. Okay, well, how many total orbitals is that? It's 4. So we probably end up needing to mix all of those. So if I take these and I mix them, I'm taking one s orbital and 1, 2, 3 p orbitals, and I get something like that. I get this hybridization of one s and 3 p orbitals, so we get this sp3 hybridization. So what are these various types of hybrid orbitals? Well, if I have linear, I need 2 places. So we have s electrons, and then we need to take p. And so my sp hybrid orbitals are going to correspond to our linear. Let me rewrite that. Okay, so our linear molecules are sp. When I have trigonal planar, I need 3 places to put things. So I need to pull that s orbital and 2 of the p orbitals. So this is our trigonal planar. Okay. For our tetrahedral situations, we need 4 places to put things. So I've got to pull the s and all 3 of those p's. Okay. Now, this ends our octet, right? Anything beyond this, we have to start expanding that octet. So what period can we start extending the octet? Period 3. Because what shows up in period 3? Our d orbitals do. Because remember, at period 3, we have an n value of 3. And I can have L values of 0 to n minus 1. So in period 3, I can have an L value of 0, an L value of 1, and an L value of 2. Our L values correspond to the orbitals that exist, s, p, d. So in period 3, those empty 3d orbitals exist. In period 4, we fill the 3d orbitals, but the empty 4d orbitals exist. In period 5, we fill the 4d orbitals, but the empty 5d orbitals exist. So once we hit period 3, we always have an empty set of d orbitals. They're not filled until we start bonding. Because once we start bonding, the atom can draw on anything that's available to it in order to make the bonding work. And so it can utilize those empty d orbitals. And so as we start to expand the octet, we have to pull the s, we have to pull all 3 d, or all 3 p's, and we can start pulling a d or more. So here, sp3d, s is 1, 3 p's, and a d. That gives me 5. 5 places to put things if I hybridize with those d orbitals. Okay, so this corresponds to our trigonal bipyramidal geometry. Okay, and then what do you think our last one's going to be? sp3 d2. Okay, and this is going to correspond to, coincidentally enough, octahedral. Okay, all right, so let's take a look at how all of this works. We'll break each one of these down and see where these electrons end up with some example molecules. All right, so when we start off with that sp situation, all right, we've got our 2s, 2p. This could all still be 3s and 3p. Okay, for here, we're just, going to deal with our 2s and our 2p. All right, so if I have something that is linear, well, how many places I need to put things? I need 2 places. So let's say I have something that only has 2 2s electrons. Okay, I only need 2 places to put things. Okay, so I'm going to grab an s and I'm going to grab 1 p. And so what I'm going to get is this mixing all right? And I'm going to get an sp hybridization here. Well, there's 3 2p orbitals, so I'm going to have leftover 2p orbitals. Now, this is going to be very important later on when we start to look at where do things go once we start pi bonding, because we're just going to be mostly looking at what's happening with those sigma bonds, remember? Because sigma bonds are how our geometry forms. Okay, because we have to have that initial end-to-end linkage. And so situations where I have stuff left over in my empty, or not empty, but my unhybridized p orbitals can give us places to put things for double or triple bonds. Okay. All right, so when I mix, I'm going to do the same thing I do when I distribute electrons in just a normal partial orbital diagram. 1 electron per, and then I go back and spin pair as necessary. Okay. All right, so if I have something like this beryllium dichloride, here's what the mixing looks like from a 3-dimensional perspective. We take that 2s and we end up getting the situation where we get our sp, they mix with each other, we're left over with those empty 2p orbitals. But you can see now, right here, when that overlaps on an end-to-end, it's linear. Okay? Okay, so this will overlap over here, and this will overlap over here, which is what you see down here. Okay, so let's take a look here. All right, so we have this. Okay. All right, so my beryllium, my valence is 2s2. So 2s, 2p. All right, and so we're going to grab this. We'll mix. And I can put electrons there and my sp and my leftover 2p. Okay? All right. And so there we get our sp hybridization that gives us something that is nice and linear in fashion. Okay? Now, how do we get our trigonal planar? What are we mixing there? Well, again, we need to mix 3 things. All right? And so here we're going to mix s and 2 of the p's. All right, so our boron trifluoride. Okay, we get something like that. We know it's trigonal planar. And so here you can see this boron. We've got this sp2 hybridization. We've got the hybrid orbitals overlapping with the fluorines, and then we have that empty 2p. All right. So we get our 2s, we get our 2p. Okay, so boron has a valence shell of 2s2, 2p1. So we get 1, 2, 1. All right, so I'm going to go ahead and grab these guys here. All right, we're going to mix. Okay. And so we'll get our sp2 and our empty 2p. And we'll go 1, 2, 3. Okay, because 3 electrons, and I have to go 1, 2, 3. And each one of those now can be paired up and give us what we see there. Now, geometrically, how does this look? Okay, so we get the S that hybridizes with 2 of the P's, and as it hybridizes, we get 3 different orbitals, and those 3 orbitals, when they overlap, give us this flat triangle. Okay? Here's another view where you can see from a top down and a side view where we're accounting, again, also for that 2p orbital that doesn't hybridize. Okay? All right, now let's go back to sp3 and our methane. Okay, so again, carbon, Valence, 2s2, 2p2. Methane, we get this. And geometrically, we get this. Okay? All right. So 2s, 2p, 1, 2, 3, 4. Again, that's not going to cut it, right? Because we don't have everything situated such that we can have 4 bonds. So now we'll have to take all of this, and this is our mix. Okay, and now I have 1, 2, 3, 4 sp3 hybrid orbitals. And I can go 1, 2, 3, 4. Redistribute all of those electrons, and there are my 4 places where I can bond with my carbon. Okay, geometrically, here's what it ends up looking like as things hybridize. Okay, and so we get this hybridization, we overlap everything, and then when we put it all together, that's where now we see that 3-dimensional shape, all right, that gives us this. Okay? Because everything's pushing each other as far apart as possible. Because again, this all goes back to the fact that electrons are negative, right? And they don't want to be next to each other. They're both negative. They repel each other. And so they're pushing each other far apart. And so when they arrange, we get this geometrically equivalent arrangement where they're all pushed away from each other. Now, once we hit that trigonal planar portion, we are able to have situations where we have bonding and we have lone pairs, right? Because in trigonal planar, we don't just have all bonding where we have trigonal planar orbital geometry and trigonal planar molecular geometry. We can have our trigonal planar orbital and we can have bent molecular. Same thing with our sp3 here with tetrahedral. In methane, everything is bonding. So I have my tetrahedral orbital geometry with my 4 places to put things. I remain tetrahedral for my molecular geometry because everything's bonding. But what happens when we have those lone pairs? Can we account for those with this theory as well? We can. So let's take a look at ammonia and water. Both of those, we start substituting bonding groups for lone pairs to get our trigonal pyramidal and our bent geometries that still fall under the tetrahedral banner because there's 4 groups around our central atom. So how do we account for our lone pairs? Let's look. So with ammonia, okay, we have NH3, right? So I have my nitrogen, hydrogen, 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 3-dimensionally. You know, we've got that, we've got that, we got that, right? Nitrogen, valence electrons, we have a 2s2 and a 2p3. So I have 2s and I have 2p. So 1, 2, 1, 2, 3. Okay, so this is still sp3. And as you can see, we're going to stick those lone pairs in one of the hybrid orbitals. So let's go ahead and grab everything we need for mixing. Okay. And we're still going to have sp3 hybrid orbitals. There's still 4 of them. Now, there's 5 valence electrons that I have to account for. So we're going to do the same thing. We're going to put single electrons in each, and then we'll go back and pair up as necessary. 1, 2, 3, 4, 5. Okay, so here is my lone pair. All right, and here are my bonding electrons. All right, were we able to put everything in a spot? Did we use all of our electrons and account for every one of them in our sp3 hybrid orbital? And did it work out such that we have exactly the number of paired up electrons we're supposed to and exactly the number of unpaired electrons we need for the bonds to occur? Yeah, because we need 3 unpaired electrons to pair up with the electrons from the hydrogens and then that lone pair. Let's see if it holds true for water. Okay, so again, we've got our molecule. And again, three-dimensionally, we've got that. Oxygen, our valence electrons are 2s2, 2p4, so our 2s, our 2p, 1, 2, 1, 2, 3, 4. Okay, we still need 4 places to put things. I need 2 bonds and 2 lone pairs. So we'll go ahead and do our mixing. We'll take all of those for a mix. Okay. And again, we have our sp3. So now I have 6 valence electrons that I need to distribute. 1, 2, 3, 4, 5, 6. So I have 2 sets that are paired up, lone pairs. And then I have these right here for bonding. All right, so did we get our 2 and 2? We sure did. So we've accounted for everything there. All right, and then let's go ahead and look deeper. Now what happens when we start using those empty d orbitals? All right, so I had to stack the orbitals like this in order of the normal increasing energy because there's only so much space on my slide. All right, so here I have a phosphorus pentachloride. I'm not going to have enough space, I don't think, to do the 3-dimensional. But when we do this, all right, we have this situation going on, right, for phosphorus pentachloride. And that drawing in the corner there, where it shows all the orbital overlapping, is in 3 dimensions. All right, so we get this. So my phosphorus, I need how many places to put things? Well, I need 5, all right? And so phosphorus, when I account for my valence electrons, I get 3s2, 3p, 3. So I have my 3s, I have my 3p, and now I have my empty 3d. Okay, so there's my 3s2, 1, 2, 3. There's my 3p, 3. I need 5 places, so I need that d or one of those d orbitals. I'm going to take all, that s, I'm going to take all 3 p's, and I'm going to take 1 d. Okay, and this is going to be my mix. And so I'm going to have 1, 2, 3, 4, 5 s, p3, d orbitals, and 4 leftover empty 3d orbitals. Okay, phosphorus, I have 5 valence electrons. So we're going to go 1, 2, 3, 4, 5. So were we able to give a spot for everything? Yeah. And then those 3d orbitals are empty and left over. Okay, and so there's a sketch of what that looks like in 3 dimensions. Okay. And then when we start looking at, other structures here, this is what it looks like 3-dimensionally as everything overlaps. We draw a Lewis structure that looks like this. Okay, and there is our sp3d where everything gets arranged around there. Okay, And then when I look at this one here, I've got this bromine trifluoride. Okay, so bromine, okay, where is bromine located? Well, if we look at our periodic table, bromine is in period 4. And so our valence here is going to be 4s2, 4p5. We have 7 valence electrons. Okay, and so we can do our 2, that's a little small. sp3d. So 7 valence electrons, 1, 2, 3, 4, 5, 6, 7, where I have my lone pairs and my bonding. Okay, so we can account for all of it. Oh, ha! I had put the lines on there for myself. Oh well, doesn't matter. I drew them anyway. Okay, and then our last, where I have 6 places to put things. Okay, and so we've got this sulfur hexafluoride. Okay, and sulfur, our valence electrons, we're going to get 3s2, 3p4. So 3s, 3p, 3d. Okay, so 1, 2, 1, 2, 3, 4. Okay, so now I'm going to take S, P, and 2 of the D's with me. We'll mix. Okay, and we'll get 6 sp3d2 orbitals with 3 empty 3d orbitals. Okay, 6 valence electrons. 1, 2, 3, 4, 5, 6. All right, so did we have enough places to put everything? Yeah. So everything can pair up, and there's our places to put things. So here's what it looks like 3-dimensionally with those hybridized orbitals. And so in summary, each one of our 5 basic molecular shapes, we have to have that many things to put, places to put things there. Linear, I need 2 places to put things. Trigonal planar, I need 3 places to put things. And so we can correlate each one of our 5 basic molecular shapes with a specific type of hybridization, where sometimes we have things left over, sometimes we don't have anything left over. Like tetrahedral, we don't have anything left over. We use the S and all 3p. But linear, sometimes we have some p orbitals left over. Trigonal planar, sometimes we have some p orbitals left over. And so those leftover p orbitals can help us figure out things where, everything I did here only had single bonds. But, when I look at something like this, this is trigonal planar. So this is going to be an sp2. Well, I have an empty p orbital left over that's going to help us explain eventually what we do with the double bond. All right, so there's our valence bond theory. We will do examples in a separate video because I know this gets long, so stay tuned for example problems. They're in the next video. I'm not just going to leave you hanging with the explanations.